네, 교수님 감사드립니다. 이제 지금부터 본격적으로 저희가 오늘 하나는 국내외 세미나를 시작하도록 하겠습니다. 첫 번째 강연으로는 야코브 파체스키 박사님으로부터 Homage to Soil and Scale에 대한 주제로 발표가 있겠습니다. Please welcome Dr. Pachepsky with big hands.
For invitation. It's a pleasure to be here. An honor to be here too. So I don't think I will tell you anything new that you don't know. But I think you may find another view at things that you already know. So let me start from this small picture. This is the main building of the university in Moscow, in Russia, where I get all my degrees, the undergraduate degree, graduate degree, PhD, doctor of science, all this. And we have this arrow. Arrow shows the window of my dormitory. And in the building, there was Department of Mathematics and Mechanics, which I graduated from. This is a experimental setup that we had, and we studied computers too. And my PhD work was already on computer simulations of underground explosions. So we are looking at nuclear bombs under surface of the land. And we wanted to create cavities, empty spaces where we could store nuclear waste or something like that. Yeah, like that? Okay. All right. Let's see how it works. Yeah, this is my supervisor, was genius person from Armenia. And it was the first time I encountered a question of scale. We had a project to create a dam in the mountains. And what we wanted to do, we wanted to blow one of the mountains at the bank and close the river with the results of the explosion. So we not far from Moscow, we tried this, and this method worked. But then we came to the real mountains, put the real explosives under the mountain, and let's see what happened here. No, it's not what I wanted. This one. But could you press this thing so it will develop a movie? Yeah, thank you. So just look what happened here. So first of all, of course, nothing will happen. And then the mountain began to blow. Mountain began to blow. Mountain began to create all this dust. And we were very happy. We thought that these rocks will actually create our dam. But when all the rocks fell, we found out that the mountain just moved from another side to one side to another. So it didn't move where we wanted. And the reason was that we based all our modeling, all our results from small experiments near the Moscow. And then when we came to the big scale, all these parameters became unvalid. And then I had to find a job after the university. So my job, first job was in Soil Institute, not far from Moscow. And average age of staff scientist was 27 years. So we were very young, very energetic, and it was a great place to work. And of course, there are old people who created big maps, soil maps, and then you can find what like watershed scale, horizon scale. So it's just a sea of words or sea of word combinations in which you have word scale. So what is scale really? Well, it appears that scale is very important and very vague. Vague means poorly defined, badly defined. Some people would define scale as a hierarchy of organization of the nature, and other people would define scale according to the measurement, like size, and other people would define scale poorly geometrical. This is examples of hierarchical scale definition. It appears that in different sciences, people define scale differently. In ecology, you can see they start with organism, then go to population, then the community, then ecosystem. And in hydrology, it's again different. They talk about local scale, hill slope scale, catchment, and regional scale. In soil science, it's yet another definition: molecular, then aggregate scale, horizon scale, and so on and so forth. So there is no single definition of this hierarchy of scales. This is different way of defining scales through the measurements. You may have support. This is a part of the land or water or any surface within which you don't consider variation. It's just considered to be homogeneous, and only single number is used to characterize all this piece of land or water surface. Then there is another measure of space called spacing. This is the distance between measurement locations. And finally, there is extent. This is the total size of the piece of land you are looking at. In this way, scale is defined by the triplet: support, spacing, and extent. So what's the difference between scales? There is a big difference, actually. If you look through the hierarchy, then you look at number of important variables. When you work at the small scale, fine scale, then you can do many measurements. Just think about a small piece of soil or small piece of anything. You can do electrical measurements, physical measurements, chemical measurements, and all these measurements are valid. But as you go to the larger scales, coarser scales, you don't have this luxury measuring all these small things, and you begin to operate with very general terms like total evaporation, total transpiration. So moving through the scales, you change the things that you actually measure. Go to the quarter scale. Further on, time scale is very important at the fine scales, but not really much at the coarser scales. Now, if you try to do modeling, and this is the essentially engineering thing, and you begin to do engineering through the scales, at fine scale, modeling is not that important. But if you go to the coarser scales, the role of modeling is actually very important. That's the only way we can obtain information which is used for forecasts, for environmental assessments of important for the policies. So the communities, society is more interested in coarser results from the coarser scales. Similarly, the mechanisms, we try to understand mechanisms at the fine scale, but if you go to the coarse scale, we have difficulty to define mechanisms. So we just describe them. And the type of modeling also changes. You can look at processes, model processes at the fine scale, but if you go to the larger scale, you basically are left with statistics and with the machine learning, so with things which do not take into account any mechanisms. Let me skip this one and give a couple of examples of coarse scale projects. I had a privilege to be involved in a couple of large-scale projects. It does not happen often in lifespan of scientists, so I consider this as a privilege. This one was a project about the irrigation in the southern Ukraine and Russia. So we are talking about 1 million hectares irrigation. And the issue was that before that, Soviet Union, as a big country, had irrigation in the Central Asia, which is far from this place. And the country had a huge problem with salinization. Water became saline, soil became saline, yields became low, so it didn't look good. So there was a serious concern that if we begin to irrigation in the southern Ukraine, we will have the same trouble. So that was the project I was involved in. And example here is mostly, what do you do with a big piece of land? How do you characterize what happens in the big piece of land? You cannot take many samples, you cannot take many images, you can take anything. So how do you operate? It appears that you can still do things, and what you need to do, you need to try to find parameters or combination of parameters which will work across large scales, large distances. So the models which existed at this point when we started doesn't mean much if you have a big territory to manage. You may look at years as your tile scale. And this is actually an interesting feature of scaling. As you increase the size of the piece of land you're looking at, you have to increase the time step you're looking at this piece of land. It doesn't make sense to look at the hundreds of hectares and have a time step of observation 1 minute. You don't know, we will not know what to do with this type of data. So there are two ways to deal with this. If you have fine scale inputs, you can go to the coarse scale inputs just to combining them and then create a coarse scale model. Or you can look at the fine scale inputs again, run the fine scale model many times, and then trying to combine results into something which will be useful at a coarse scale model. So maybe I'm not going to go into all these details now. What I want to say that there are methods which allow to decrease the number of parameters that you can use to describe your system. This method was actually invented by Galileo Galilei in 400 years ago, and he wrote a book in the end of his life when he was already the engineering courses he will study. But what's important to know that using this system, this theory of dimensions, you're getting very simple and at the same time very efficient dependencies that you can use at the big scale project. So there are methods. We are not helpless, but we need to use these methods sparsely. So what are the features of the coarse scale modeling project? What did I see? What did we see? So first of all, we need the need in the modeling is supported by regulations made by the government. This is the situation in which government or some agencies or some communities require modeling. Second thing is the modeling is has to address engineering design needs. So you can't just describe things you want. You need to describe what engineers can do, and they not necessarily can do everything. You are future engineers, you know that better than I do. There should be correspondence between temporal and spatial scales. I mentioned this. A model has to be simple and robust. And finally, the maximum use of observation has to be in place. Anything which was observed has to be used. And I had a very strange example of this. We rely on multi-year data, and we didn't get any results. So I was desperate. And my director said, okay, go talk to old people. So I came to talk to old people, and it appears that 5 years ago, climate in this area suddenly changed. And the multi-year observations did not cover this. Local strong climate change was not in the records. And as a result, we had the trouble to compute. So you do need to talk to people when you work somewhere and to here what they think about the nature in this area and how the nature might change. This is another example. It's agro-ecosystem design to combat the drought. This is the area in the central Russia called Kamenная steppe, which is stony steppe. That's how it looks every 3 years. Nothing can grow in this land because of the drought. And there was an institute in which we worked to figure out how people were able to deal with this. This gentleman whose the monument is here, he established soil science as a science. But before that, he was invited to this area to resolve the issue with the droughts. And if scientific solution for this area to create a very wide windbreakers. The role of these windbreakers was that they collected snow during the winter, and then snow under the trees wouldn't melt immediately, so it was melting gradually, and this water would come to the fields from under the trees, and the fields were small, so the seeds had time to water to germinate. And after that, they could already get a decent yield. And besides, there were, of course, the ponds to which water would come because it was saved. And then the animals would be able to live there, and therefore there was manure. So the fields could be manured. So this is a simple and efficient system. And couple of lessons for this project were first, we did the modeling, and modeling was useful, but it was useful at a finer scale than before. Then use of modeling was to evaluate design detail, so how wide have to be these windbreakers. Then there was the interaction with community, and it was not easy in those times because these windbreakers would take land from the fields. So there was fields were much smaller, and the peasants were not happy with that. They say, okay, we are losing land, so we will use yield. And finally, there was this interaction between engineers, really, because this is an engineering solution of the large scale. And community became very important. And the third example is from the Central Asia. That's the cotton producing area. There was, and still there is, Aral Sea. It's a huge lake in the middle. And this lake was drying. So you can see that there is a ship in the middle of the desert and camels looking at it. So this drying was because water was used for irrigation. And so it did not come to this Aral Sea. And then, sure thing, people decided, okay, we can do something about it. We can take water from Siberia, which is this one, and move it to the Central Asia. And they decided to build a canal, which is about 2,500 kilometers, a huge thing, really. One of the biggest projects probably on the planet. Okay, so what happens after that? First of all, first things, I didn't want to do this project at all because I didn't have any idea how to deal with this type of size. But eventually, I was kind of forced to do this. And here's the precondition. You may have a rise of groundwater. You're losing fisheries. You're losing many things in Siberia. You're changing flora and fauna. So there are pluses and there are minuses in each big project. You had the same thing here in Korea with the rivers, which are connected between each other. There are pluses and there are minuses. It's unavoidable. So what we found that there is no certain answer. Is it good or is it bad when we will move this water from Siberia to the Central Asia? You may have water coming salty. You may have water coming okay. You may have water lost in Siberia. So uncertainty was so high that we couldn't give a specific answer. And this was not really what was expected. But that was the best we could do with the data that we had. So then there was a political implications of big project, as always it happens. In the end of the day, this project was closed. Now they don't build anything like that. Important issue I would like to touch is how do you move information between scales? Because we are measuring at fine scales, right? We don't measure at the big scales, but the difficult for us. Nowadays is better because we have satellites, we have imagery, but still to define something for the big piece of land is very difficult. So we measure small stuff. And the example I want to give you is this. If you want to look at the ability of conducting water at the fine scale and the horizon, when the samples are small, you can measure a value which is called hydraulic conductivity. And it depends on the suction, depends on the water content in water. But if you go to the coarser scale, you have only permeability class. You are characterizing the same property of soil. You just do it at different scales. And then you have different values, different measurements. So is there any way we could move from the fine scale information to the coarse scale? Let's see what people try to do. They wanted to move information for the small scale about the ability of soil to store water. So they said, okay, let's set a value of suction at which water content is measured, and then this will be our water holding capacity at what scale. So, Input 5 kilopascal. Passport of the United States, 33 kilopascal. Passport of Brazil, 6 kilopascal, and Sweden, 20 kilopascal. So it cannot be this way. The result of these measurements is so different because people will just have small databases and they were using them to derive a single number, which shouldn't happen. But then it's an important question, okay, what to do? We measure things at the fine scales. We cannot measure things at the large scales, and we need to have some way to transfer information from the fine scale to the coarse scale. And to do that, the only way which was more or less successful is to look at patterns. So what pattern is? Pattern is a feature which is repeatable. You can see it again, again, and again. And knowledge about patterns appears to be invaluable for diagnostics, monitoring, prediction, and controls. And here's the small example, simple example. If you look at, say, for Canadian way of defining permeability of soil class, you do use this information about the final scales, but at the same time, you use information about the patterns which you observe on the coarse scale, at the scale where you want to move the information. And those patterns are called soil structure. You see it again, again, and again, how soil is organized in space. And you use this information together with information for the finer scale to get information that you need. I will skip this one. And let's look a little bit at the patterns at the horizon scale. There's a very simple method to recognize a pattern. It's called temporal stability analysis. You come into the piece of land or to the pond, we did it for the water. You measure a variable of your interest. In our case, it was concentrations of E. coli. It's a bacterium which is used to evaluate microbial water quality. And then you compute relative difference. Here's this simple equation in the corner of the slide. Your relative difference is the value in this location minus average across the area divided by the average. And I do this, you do it one again, you come in again to this area, do the same measurements, and then you compute average relative differences. And as soon as you do it, you have mean relative difference on the vertical scale. And here is the horizontal, here is the horizontal scale. So you can observe this S-shaped curve, which shows and this is a spatial pattern because we look at the differences in space. And this pattern preserves itself in time. So it appears that this, what they call temporal stability, is actually a very common thing. Here's another pattern related to the microbes, which I don't think I have time to stop to consider. Here's another type of scale dependencies that we can discover if we change the support, the size of the area that we measure. So we define scale not with the hierarchies, but we define scale with the size of the geometrical size. Here is, for example, just for example, This one is hydraulic conductivity of soil, so ability of soil to conduct water. As you increase the size of your sample or piece of land where you measure hydraulic conductivity, we have the increase of hydraulic conductivity, and then it stabilizes. Same happens to other parameters which control transport of mass and energy, mostly mass, in the field. So why it is important? It is important because you say you're working with some model and you need to find parameters of this model, coefficients in your equations. So you use the measurements and then you find these coefficients or parameters. Units of space. Then you are coming to different field, different field. And what to do with this, you need to take special precautions. That's what happened with us with this experiment with the explosion that we saw in the beginning. We measured parameters on the small pieces of soil or ground, and then we used these parameters for the bigger scale, and we failed. So let us keep this one and talk a little bit about challenges. So challenges here are, one of the challenges is a big data. Now, you're engineers, you know better than I do, that we have capabilities that we couldn't even think about to create huge data sets. We are getting them from remote sensing. We are getting them from the proximal sensors, so when your sensor is close to the object. We are getting it from the imaging, all kinds of omics, genomics, molecular biology, gives us huge databases, sensors. So this is a new source of data. Okay. So what do we need? We need to understand what to do with this massive material. So it looks like we have the issue of scale coming to our data collections. So we need to aggregate this data somehow so that we actually can look at it. This too. And so we need to understand scale in data, which we didn't really have this problem before, but now it is serious. And there is a timeline, what people try to do. So in 80s, which was a long time ago, they would use important inputs in some automated way using the stepwise regressions. And they went from complex mathematical constructs to extract it. But in the end of the day, they found that at this point, we need to aggregate embedded and related inputs to outputs. So we are coming to deep learning, we're coming to the neural networks of specialized types. So there is the evolution is going on, and it's going a fast way. This evolution basically, in some way, always is related to the question of understanding scale in data. It's understanding scale and pattern relationships becomes really important. And we will see more and more examples of this, because patterns is something we can observe. And this is very important. still we can't measure some parameters at coarse scales. Say we can't measure hydrophilic contact. Example, we need to define structure for scales. We don't always can do this. At this point, for example, in soil science, we know that there are such a thing as soil associations in soil cover, but it's uncharted territory at this point. Network patterns, that's another thing which we don't know much at the coastal scales, and they are related to the connectivity in landscapes and landforms, which we need to know. Patterns is a result of some kind of optimization. They don't pop up spontaneously, no. They are a result of some processes which are happening at the lower scale. And there is some kind of criteria of optimization which this pattern demonstrate to occur. Which is very important to know when to see if and when pattern breaks. Something happened in the system and happened something serious, otherwise pattern wouldn't break. So that's a very good sign for detection changes, which may be good or bad, or we don't know. But we need to see if this break occurs. So all in all, patterns, we would like to reproduce patterns with models. We don't really know well how to do this. That was showing came up from the interactions and collaboration with large number of people, whom I very thankful. And I hope that you will look at material that you know, learn, and you work with from the point of view of scale and pattern. And thank you for your attention.
네, 네, 수고해주신 우리 파체스키 박사님께 다시 한번 큰 박수 부탁드립니다. 혹시 질의응답 가지신 분이 있으시면 좀 얘기해 주시면 좋을 것 같습니다. 저희가 마이크를 드리면 저희가 동시 번역이 되기 때문에 좀 편하게 질문하셔도 좋을 것 같습니다. 만약에 혹시나 추후에 생각나시는 질문 있으시다면 적어 두셨다가 추후에 한번 얘기를 해주셔도 좋을 것 같고요. 네.
First of all, thank you for your presentation. This is Kyun Bang under Professor Beck.
Sorry, I don't hear. Could you keep it close, as I did? Thank you.
Okay. First of all, thank you for your excellent presentation. This is Kyun Bang under Professor Beck, and I have a question about applying deep learning in soil part. In terms of technique, is it possible to discover patterns at the aggregate scale? I mean, in very fine scale.
Patterns are usually discovered from a geometrical point of view, typically. So you represent data that you have in some geometric way. And then you try to use geometrical metrics or measurements to see if there are repeatable features. The one I was showing, which is called temporal stability, there are more complex, mathematically complex tricks called empirical orthogonal functions. There are other mathematical methods. They are coded. They exist in the libraries of R language, of Python. So it's not something you need to code yourself. Using them, you are getting a really good really good feel about the data. And then after that, you decide, okay, what I'm seeing is a pattern or it is as a fluke. So then you can add other data to see if there is repeatability. So from my perspective, maybe I'm not sure if I'm wrong, maybe or right, but I think it's first of all, it's a geometrical perception.
Okay, thank you so much.
The project, the project was officially closed in 1986. That's the Communist Party meeting, and it was very interesting because we had a movement of Greens in those times. So there was a perestroika, there was political changes in the Soviet Union, so you could be more free. And the Green movement saw large danger in this project. And our report actually was found. Frankly, I almost lost my job because of this. But at any rate, they found it later, and it was decreasing, and moving up political ladder, came to the top. At the end of the day, Russia said, we will not give this water. And until 1999, nothing was happening. But then this project was revived. And there were, again, plans to move this water from Siberia to Central Asia. Again, it appears that there were no resources in those times to do this. Now is the third round. Kazakhstan and Uzbekistan, especially Kazakhstan, requires this water from Russia, and Russia doesn't want to give this water. So I don't know what they're going to do with this, frankly. So at this point, I saw three.
Project. So if in your modeling result that it means that the salinity problem around the RRC can be resolved if the water is just supplied through the artificial canal.
Could you repeat, please?
Yeah. Because I just wonder the result of the modeling about the RRC. So if the canal is established between Siberia to RRC, then the salinity problem around the RRC going to be resolved or not?
Here's what the big size problem there was this. There was not enough of concrete to build this thing. So the water had to move in the ground. There should be a big piece of canal, about 30%, where the influx of saline water could occur. Could not, depending on hydraulic properties of grounds, which we don't know well. So the results of our project, that's one story. Another story was that about 40% of this was moving through the area where the water simply could be lost. So it wouldn't come at all. And again, we didn't have enough information to make a conclusion that this water will go. So the result of this project really was that uncertainty is so high that we can't say anything. And people didn't like it. But that's what happened in those times.
Thank you so much.
네, 또 혹시 다른 질문 저희 학생들 중에 혹시 한 분 있으시면 해주시면 좋을 것 같습니다. 만약에 없으시다면 저희는 이제 다음 발표로 넘어가겠습니다. Thank you, Dr. Pachepsky. So we're gonna move to the next presentation. Thank you so much.
Thank you.